welcome to another episode of Chemistry. Today we're going to talk about how to use the electrochemical series, specifically for redox. All I want you to do is to become really confident at reading one, trying to use it to figure out spontaneous and non-spontaneous redox reactions, as well as identifying the half equations that are occurring in these redox reactions. Now, when it comes to the spontaneity of reactions, I'm specifically talking about redox reactions. So we're going to go from chemical to electrical energy. When it comes to non-spontaneous reactions, it's going from electrical and converting that to chemical energy. And so what we can do is actually use what's called the electrochemical series to both predict and to write the half equations for the redox reactions that are occurring. So what does it look like? Now, this is just one example. I've just cut off a little bit of an electrochemical series. The first thing you'll note is that this electrochemical series is actually a series of reduction reactions. So you can see here all of these elements, all of these species are gaining electrons, reading from left to right. So all are reduction reactions. They've also got these, what we call their standard electrode potentials. I'll explain that a little bit later on as well. So here, really just a representation that all of these species are undergoing reduction. If you draw a line just before the double arrow, everything on the left-hand side we would consider as oxidizing agents. So here, F2, peroxide, permanganate, lead oxide, that sort of stuff. All of these guys are your oxidizing agents, and the things on the right-hand side are your reducing agents. So fluoride ions, chloride ions, water molecules, silver solid, those guys are all reducing agents. What they also do is they give us the strength, so that's ordered in strength. In terms of the oxidizing agent, the strength of the oxidizing agent increases from bottom to top. So what we see here is fluorine is the strongest oxidizing agent. And then looking at the reducing agents, the strength of it increases as you go down the table. So from what you see here, lead solid right now is the strongest reducing agent that we see on this table, but it's not for the full table. So that's the general pattern. The other thing that you can look at are these numbers. Now, each of these numbers represents how likely the oxidizing agent is going to undergo reduction. So the higher the number, the more likely reduction will occur. That just means that the oxidizing agent is really strong. Essentially, it's really, really, really likely compared to all of these other oxidizing agents that fluorine will gain 2 electrons to form fluoride, more so than bromine gaining 2 electrons to form bromide, right? So these numbers can also be used to indicate how likely is that substance or this reduction reaction going to occur. How do we use the electrochemical series for redox reactions? For redox reactions, regardless of what type of redox reaction you're looking for, you're always looking to pair the strongest oxidant with the strongest reductant. I don't care what type of redox reaction we're talking about. As we know, the oxidant or the oxidizing agent undergoes reduction. The reducing agent undergoes oxidation. That's how we use it. We're always looking for the strongest pairs. So from what we see here right now, if I had to pick the strongest oxidant or strongest oxidizing agent, this is the strongest oxidizing agent that I have right now from what I see. This is the strongest reducing agent. This is my strongest oxidizing agent, and that's how I want to do it. I want to find the pairs that are the strongest oxidizing agent, the strongest reducing agent or reductant. Now, we can use the electrochemical series to figure out the spontaneous reactions. For a spontaneous reaction, the E0 value, so everything in this column here, of the oxidizing agent needs to be higher than the E0 value of the reducing agent. If that's not the case, it's a non-spontaneous. If it's not, it's a non-spontaneous reaction. So for example, what we said before, let's just say I want to react fluorine gas, so that's my strongest oxidizing agent, with lead, that's my strongest reducing agent. Now if you compare the two values, the strongest oxidizing agent has a value of plus 2.87. The strongest reducing agent has a value of negative 0.13. Now, because this value here for the strongest oxidizing agent is larger than the strongest reducing agent, that means a spontaneous reaction will occur. So let's do an example where we use the electrochemical series to try and figure out whether or not a reaction is going to be spontaneous. Now, the question is asking us, hey, we need to identify if a spontaneous reaction will occur if you put nickel solid into a solution containing copper sulfate. So what that looks like is, let's say you've got this, got a piece of nickel in there, and in there you've got copper sulfate solution. And this here is nickel. Cool. All right, let's go to the electrochemical series. And all I want you to do is to circle everything that's involved in this reaction. So before, what we had here was nickel solid. We had copper sulfate solution. Now, for a copper sulfate solution, you know that it's actually separated into its ions of copper 2 plus, as well as sulfate ions. And to make it aqueous solution, you also have to have water. All I want you to do now is to go to your electrochemical series and circle everything. Every time you see nickel, every time you see copper, sulfate, water. I'm going to give you a head start. You're not going to find sulfate ions in here. It's not going to be involved in the reaction. So let's go ahead and circle or highlight every time we see any of these three species. All right. So you can see what I've done here. Let me just zoom in again. I've gone ahead and highlighted all the instances I see of all of the species that I identified, right? I know that everything on the left-hand side, there's an increase in strength of oxidizing agents. On the other side, I have an increasing strength of reducing agents. Cool. So right now, all I want to do is I want to pick the strongest oxidizing agent and the strongest reducing agent. Now, according to what I see is the strongest oxidizing agent, top left, water. My strongest reducing agent that I've circled, as you can see highlighted in the yellow, is nickel solid. Now, for a spontaneous reaction, this needs to be true. The E0 value of the strongest oxidant has to be larger than the E0 value of the strongest reductant. The strongest oxidant that we've identified here is water. Now, for that to be true, for water to gain 4 electrons, it also requires oxygen, as you can see here, going from left to right. Now, we're talking about oxygen that's added additional, not just what's in the air. And you can see in our sort of ingredients list, we don't have oxygen as an additional reactant, so I can't consider this. So I go to my next best one, and it's going to be copper. Because if you look at this, the only thing that copper needs for this reaction to be fulfilled is the electrons that it will gain as part of reduction. So we're all good there. So the E0 value here of copper, so this is my strongest oxidizing agent, that's right, and that has an E0 value of 0.34. Then I go and I look at my strongest reducing agent, which is nickel here. Now, my strongest reducing agent has a E0 value of negative 0.25. Now, is it true that this value is bigger than this value? The answer is yes. As a result, when I dip the nickel solid into the solution, a spontaneous reaction will occur. So we're going to go, yes, it's spontaneous. So the next part of this is, okay, well, now that we know it's a spontaneous reaction, how about we go and try and figure out what the half equations are, the oxidation and the reduction reactions for this reaction when you have that nickel being placed in a solution of that. I want the half equations. Now, if we go back here, we can use this electrochemical series that we've drawn all over. Now, we know that the strongest oxidizing agent, the oxidizing agents in general, undergo reduction. So what that means is copper will go from left to right. It will undergo reduction. You look at the strongest reducing agent, that's going to go backwards there, which means it's going to undergo oxidation. So by that, we can start looking at this and write the half equation. So we know that copper is going to undergo reduction to form copper solid. We know that nickel is going to undergo oxidation into nickel 2 plus and 2 electrons. Make sure I put my states in there as well. So that's why it's really handy to be able to know how to use an electrochemical series, because not only can you pick the spontaneous reactions, you can also use it then to try and figure out if it's spontaneous, that means that the oxidant is going to undergo reduction, the reductant or reducing agent is going to undergo oxidation, and we can use that. So it'll go from our strongest oxidizing agent goes from left to right and undergo reduction. The strongest oxidizing, we know that the strongest oxidizing agent will go from left to right. The strongest reducing agent will be oxidized, which means this reaction goes in the backwards direction. And then all we need to do is just write it in the way that it should be, like this. So this is reduction, this is oxidation. Cool? So notes about the electrochemical series, all of the data and all of the ranking that's in the electrochemical series is based on using 1 molar solutions at 25 degrees. If you fluctuate from that, sometimes you can get a different result, so be careful. The other thing is that the electrochemical series cannot predict rate. So it can't predict how quickly a reaction will occur. It can give you an indication as to whether or not a reaction will occur spontaneously. All right, so in summary, redox is always about the strongest oxidant and the strongest reductant. The oxidizing agent is found on the left-hand side of the double arrow. The reducing agent is found on the right-hand side of the double arrow, where the strength goes from bottom to top, and the strength for reducing agents goes from top to bottom on the right-hand side. For a spontaneous reaction to occur, the E0 value of the oxidizing agent has to be larger than the E0 value of the reducing agent. If it's not, then it's a non-spontaneous reaction. Cool? Right. Awesome. All right, thanks for hanging out with me today. I hope that was useful. And always remember, no matter what anybody says, yeah, you can.